So in this video, we're going to talk about some of the pragmatics when it comes to decision making about setting up a computer adaptive test. And a lot of this came out of my own work, like I mentioned previously, working on with Provisor slash SHL and setting up their system with Britt Strasgale. We had a lot of input in how it might work. Other parts have come through my own thinking about how it might work when I've set up my own adaptive test for consulting work and things like that. So there's a few questions you have to ask here, and we're going to kind of walk through some of these individually and talk about different strategies you might take or different approaches you might use to answer these questions. So here's some of the things, we talked about sort of the general algorithm. You figure out which item you want to present, you present the item, you score the item, you compute data, and then you pick another item based on that data, you revise data input, and then you repeat that cycle over and over. So it's not really that complicated. But the devil really is in the details about kind of how you actually implement those decision processes. How do you specifically pick an item? How do you start the test? How do you stop the test? How are you going to estimate ability and things like that? So let's talk a little bit about how you might do this. And the first decision you have to make is how to choose an initial item. So, one way to do it is to present the same item to everybody, right? So you've got an item that's kind of moderate in difficulty and has a really high A parameters. It's got tons of information. It's a very good item, and it might make a really good candidate for an initial item. The problem with that, and actually this kind of a problem plagues the selection of the subsequent items too, is something called item exposure. And item exposure is exactly what it sounds like. It's how often an item is presented to different candidates. So one of the things you have to consider before you really go down this path is what's the nature of your test? How high stakes is it, right? So let's think about stakes on a continuum from low stakes to high stakes. And the low side would be, just for fun, Facebook quiz or something, giving people feedback on their personality, just for their own information, or something along those lines. It'd be a very low stakes kind of test. At the other end of the spectrum, you would have something like the bar exam, right? A certification exam such that somebody who spent hundreds of thousands of bucks going to law school can't do their intended career unless they pass this test. So, and then employment test, I would argue, is somewhere kind of in the middle of those two things. Probably somewhat higher stakes, but not, not to the extent of like a CPA exam or a bar exam or something like that. So, so with any kind of, and the reason this is important is because the higher the stakes the exam, the more pressure there is to cheat, right? And cheating, um, don't be confused about this. Like cheating is it's a business, right? There are um, a lot of money tied up in the cheating industry. There are companies and organizations and people that will pay examinees to go in and memorize items and come back and report what those items are. That will, attempt systematic hacking attempts on systems to gain access to the items. Um, just lots of different things like that. And bigger companies, even in kind of the IO space, will have, kind of people or branches or services or contractors hired with the goal, and their whole job is to go out and find out, what parts of their intellectual property and their content of their exams are out on the internet. It could be buried deep in web forums. It could be, kind of again these organizations that you can pay to get access to items if you're a cheater and an examinee. So it's big business, and as a result, and obviously things like the GRE, SAT are also quite high stakes. So you really have to protect your item exposure if you are the test developer. Items are really expensive to develop. So Joe Michael, who retired from NC State, spent some time, and I think maybe Lynn Baker Ward did too, writing items for either College Board, SAT, one of those groups. I can't remember. But essentially, each item would take, sometimes hours to generate. There's a huge checklist of different aspects that it had to have. The distractors had to be just so. The items had to cover certain content domains. So, there's a lot that goes into writing items. They're very expensive to develop. If you're paying subject matter experts, $200 or $300 an hour, and it takes them, let's say, 5 hours to write an item, and apparently that's on the low end from what I've been told. You're talking about something like $1,000 an item. So if your item is out there and you presented an item enough, you can sort of assume that people will know the answer to it, right? So people will tell each other, they'll talk about it, they'll and you've seen this in your own dealings as a student. After an exam, you talk with your friends about what was on the exam. So you have to worry about item exposure. You don't want to present the same item over and over and over because eventually it no longer works, right? People aren't responding. You're no longer measuring data. What you're measuring is just nothing because everybody knows the answer to it because it becomes kind of common knowledge at that point about the answer to your first item on your exam. And that's true of other items as well. So it's not just your initial item. It's something you have to worry about. So we have to find a way to choose an initial item, but we probably don't want to use the same item over and over and over. So there's a few different ways you can do it, and other things kind of might factor into. We didn't really talk about, but setting up your item bank, as I mentioned before, you want something like 2 to 3 times the number of items in your item bank as the number you plan on presenting, right? So if you have 50 items as an upper limit for what you're going to present, you probably want about 150 items in the item bank. So you're going to generate even more items than that because obviously not all of them are going to make it in the item bank. Another thing you want to do is you want to make sure any item that goes in your item bank is a decent item. It should have a good A parameter. It should have, kind of strong psychometric properties from classical test theory. The item total correlations, which is a lot like the A parameters, should be high, and it needs to be content valid as well. So these are all things that need to be present in your item bank, and what you want is for any item in your item bank to be suitable. Right? You don't want to have bad items in there that you don't really want to present to people. That's not useful. So how do you choose an item then? Well, one way to do it would be to just randomly pick one. And so one of the things I might recommend is to randomly pick an item with a difficulty somewhere between negative zero point 0.5 and positive zero point 0.5. Now, this is assuming all the items in your item bank have a decent A parameter, so you're going to get some good information there. And the reason we're doing this is because if you select only the item with the highest A parameter, it's always the same item, right? So if we kind of randomly choose within that range, then we are able to better balance our item exposure. The other way to deal with item exposure, and this comes up again not only with initial item, but choosing any item to present, is to make some kind of algorithm. So an algorithm that considers how often the item has been presented, and essentially what happens, you're picking the item in part based on how often it's been presented. So you make literally like a weighting parameter that goes into the item selection algorithm that I'll talk more a little bit later. And that's another way to make sure you're not presenting the same item over and over and over. We'll talk about that when we talk about how to choose items. So once you've got your initial item, you have to figure out how you're going to estimate ability. We haven't gotten into it too much, but the Bayesian methods will let you score and get a theta estimate even for a single item. Now, obviously, it's not a very good theta estimate, but it doesn't run off to infinity like it did in the exercise we did in class with basic maximum likelihood. So one of the Bayesian estimates methods, and they're all equally good, the EAP, expected a posteriori, is a method that I've done, I've programmed. We'll look at the code for that later in the semester. That one's pretty good. It's non-iterative. Some of the other Bayesian methods are iterative, so they consume a little more resources, take a little more time, whereas the EAP is a non-iterative process. So that one's a pretty good bet. It's Bayesian, which is actually, most all IRT scoring is Bayesian, to be honest, and there's good reason for that. But it's a commonly used algorithm. Most all software has an algorithm for it. It's not super complicated, even though it sounds like it is. And hopefully we'll get to that in the next unit. But that's a good choice. And what that'll let you do is it'll let you score the same algorithm even for the first item. Otherwise, if you're using like the maximum likelihood, like we used earlier on the class activities, you really need to get a handful of items where you can start computing theta using that algorithm, right? And so you'd have to get 4 or 5 items or something like that, or at least until somebody gets all of them, is not getting them all right or all wrong, and then compute the score. So the AP, like I said, we're going to talk about a little bit more later on, but essentially what it does is it computes the likelihood just like we did in the class activities and exercises earlier, but using a slightly different version, using something called the Newton-Raphson procedure. It's an iterative procedure, and it multiplies it by the prior distribution to get the posterior distribution. So again, all this will make more sense when we get to it. I don't want to go too much in the weeds just yet. So, all right, we've got a theta score. Then we need to select the next item. And the best way, the most efficient way to do it is choosing the item from the item bank that has the most information from that estimate of theta. So let's imagine we start with a theta estimate of 0. We get the first item. The person gets it right. The new theta estimate is 1. just for hypothetical sake. So what we would do is we would take a theta of 1 and we would plug it into the formula and compute item information for every single item in our database um, at a theta of 1. And then we pick the maximum value. And we did something, very much like that in R, so you kind of know how that works. And you would just code that into your algorithm to do it that way. It's not, it's not very hard actually to do that. And so you could do that. But the problem is you tend to pick the same items over and over and over, and especially the first few items, right? So because after the first item, if people get it right, anybody gets it right, it's going to the same theta, and then you're going to use the same item, second item for that person. And and so what you end up with the first 4 or 5 items tend to be seen over and over and over. It's a lot of item exposure there. Um, and so for that reason, you might not want to pick the item based on the information alone. Now, the most efficient method of computer adaptive tests, the thing that's going to get you to the best estimate of theta the quickest is always choosing the item to present with the most information. But you really, in practice, you run into these pragmatic concerns about item exposure that's going to make you do things in ways that maybe aren't, the most efficient or the best, but they balance the overall needs best, right? So the overall needs include not just getting to theta quickest, but also protecting your intellectual property and your expensive items in your item base and not giving the same exam items to people over and over and over. For that reason, we're going to look at some other rules as well here. So I want to give you some examples of how you end up picking the same items over and over and over, because it may not be obvious why that would happen. So let's imagine you've got an item bank that looks kind of like this. I'm going to make all these things, maybe like in the same area of theta, negative zero point 0.5 to zero point 0.5, just to kind of see, what's going on here, maybe 0.2, something like that, 0.4. Let's just change these around. And I'm just going to put in some plausible values for these different items that we're looking at here. And let's do like 0.18. These things are rarely 0.2. So this is pretty good. So now let's imagine that we've got all the items are suitable. So, it looks like this, but we've got one kind of strong item, 1.5, let's say. And look at this. So maybe not even that strong, like 1.4, let's say. So imagine you've got this in your database, your item bank, and all these items are kind of centered around, more or less the same location. This one's a little far off. Let me make it more like 0.25 just to kind of get it over there. And so your algorithm says, okay, we've computed theta for this person. Theta is, let's say 0.2 or so, right? So, somewhere in this area right here. We need to pick the item with the most information for this person. And what you see is item 3 actually gets chosen kind of a lot, right? So anybody, if these are the only 4 items kind of to choose from around this area of data, or even if it's not, there's almost never that you'll end up picking item, let's say 1 over item 3. And in this case, item 1 may be never picked. It may not come up, at all, because these other items always have a little more information. It's still a good item. It's got a good A parameter. It's got a good B parameter. C parameter is not terrible, but it just doesn't have the information that item 3 has. So even though, like, if your theta was 0, which item 1's B value is 0, you still end up picking item 3 because even though it's centered a little higher, it's got a lot more information at theta 0 than item 1 does. So this is sort of how you end up choosing the same items over and over and over. Items with high A parameters tend to dominate, so you end up always picking those. And that's kind of what I meant by saying item exposure, right? You're always going to find the same items over and over and over because there's relatively limited context under which you ever end up picking item 1 or even item 4 here, right? It just doesn't come up much. So you end up with the same items over and over and over. So what are some alternatives then to choosing the item with the highest information? Well, there's different ways to do it. Like I said, probably the most elegant way and sophisticated way, but also the most complicated way is to pick your items based on not just item information, but a composite score. That's maybe item information times or plus some kind of weight, right? And the idea is and usually it's an inverse weight, so that the more you set up a database and you track how often an item's been presented. And the more often it's been presented, the higher the weight, which becomes like an inverse, on that item in the item selection algorithm, right? So it's no longer choose the item with the most information, but choose the item with the most of this composite score, which is item information times, 1 over exposure or something like that. And that tends to control the item exposure. That makes it sort of more equally likely that you'll pick some of the items with maybe somewhat less information, but have been seen less often. That's probably the best way to do it. You can use a kind of a simple way. You can also just match based on whatever the theta is. So this is an algorithm I've seen in practice. You've got theta, and then you just look at the B parameters, presuming all the A parameters are suitable, and you just pick the item that's closest to has a B parameter closest to theta, and you just compute that, and it's super simple to do that. That also can run into trouble if you have a bunch of items. Like imagine you've got items where the B parameters for 4 items is 0, 0.05, zero point 0.1, and then 1. So 0 ends up getting picked for kind of a large range. Anything below 0 and the 0.1 gets picked a lot, or the highest one gets picked a lot. Anything above that, and the ones in the middle don't get picked as much. So it's not ideal, but it does work. You can also say I'm going to set up a range, maybe like I'm going to take theta plus or minus 0.25 and randomly choose an item within that range. That can be done too. The only thing is you have to set up rules. Then we'll say, well, what if you don't have, what if you don't have an item in that range? You have to have some kind of fallback rule. Another thing you need to do that's kind of a pragmatic concern is you need to track what items you presented and rule those out, right? So you don't want to present the same item twice. So you've got to make sure when you're doing this that you kind of you set up usually what you do is you'd set up like a list. You would rank order all these items based on these rules. Then you would say, all right, let's take the first one, how we presented it. If not, then present it. If yes, then go to the next one. And you would keep doing that until you get, a new item now. So these are different ways to select the item. That's a really important part of the algorithm. So one thing we haven't talked about much is content validity. So it's a little bit rare for a test to be strictly unidimensional, right? So from a psychometric perspective, that's okay, but from like a content validation, validity perspective, I/O perspective, it may not be okay. So let me give you an example of that. Let's say we're gonna select employees, managers, let's say, based on general mental ability, and we want to use a quantitative ability test to measure that. So one of the issues that comes up with that is that quantitative ability is not strictly unidimensional. It's unidimensional enough to use IRT and CAT, but there's a lot of different aspects that go into that. It could be basic arithmetic, there's algebra, there's trigonometry, there's geometry, there's calculus, and God knows what else that may be all fall under the umbrella of quantitative ability that are all similar enough you can treat it as sort of unidimensional, but you don't necessarily then want to be giving the same, you don't want one examinee to get all the algebra questions and another examinee to get all the geometry questions, because then you're not really equating the content based on those things. So typically, you would set up some kind of content validity rule in your item selection algorithm. So you're asking not only does it have the most information, has it not been presented too often, but have we already presented too many items from a particular content domain? So I've seen people do this with like selection tests, and I've helped companies do this a little bit, where they've got different kind of job knowledge, maybe so it's a job knowledge test, and you've got different aspects of job knowledge that you have to measure, and you may want to make sure that you are kind of making sure everybody gets kind of equal numbers of job knowledge questions from each of the knowledge domains, right? And that's the goal. So yeah, so that's something else you have to worry about. And over here, I just got a little more information about how that works. So you set up a temporary max number of items per content domain. And if you've already presented too many from one domain, then you just move on to the next domain or something like that. Other thing you can do is after each item is administered, estimate the ability and create a rank order list of potential items. And then, like I said, you follow through with these things. If it's already been administered, you skip it. If its content domain's not been met, you administer it. If it has been met, you go to the next domain. Also considering, kind of the item exposure. So how do we know when to stop? Well, there's sort of two things you'd usually do. The biggest one is based on the standard error. That's the one that makes the most psychometric sense. That's usually what you want to be doing is, looking at and making sure that you've got a reasonable standard error. You've got some precision in your estimate that's suitable, for you. So that's the biggest thing you would do, but you have to also set up some kind of fail safe because if people respond in really inconsistent ways, like if they miss a bunch of easy items, get a bunch of hard items right, then sometimes you have trouble converging on their estimate. And that should never really happen with good items and people that are not cheating or faking or whatever. But typically speaking, you want to set up some kind of fail safe, right? You don't want people to go on and on and on forever and see all your items and get frustrated and quit. So you'd say something like, if you get to 50 items, just stop, right? No matter what. So usually set up that, and then beyond that, if that rule hasn't been met, then you would move on to a precision-based rule. And again, this is going to be something like standard error. You can do it based on amount of change in theta estimate. That's a lot like standard error. It just makes sense to compute standard error. It's easy to compute. You all did that in your homework. So you compute the standard error, and when it gets below something like 0.33 or something like that, and you can set the precision, right? Then you stop it. And what that means is different people get different numbers of items. Somebody who is consistently missing harder items and getting easier items right, you'll converge on that quicker than somebody who occasionally guesses and gets a hard item right, and misses easier items, then they're going to converge less quickly. So different people get different number of items, but hopefully they all have very similar precision in their estimate. So another concern you need to worry about is how to report the final score. So, we do this on a theta metric, but that doesn't mean anything to most people. And so when you're presenting your results to hiring managers, things like that, you can transform it. That's typically what people do. You can add and multiply numbers to it. So commonly you might do something like multiply it by some number 10, let's say, and then add 50 to it, and that puts it on a kind of a metric from where 50 is the mean, and then the standard deviation is essentially 10. So whatever you multiply it by becomes the new standard deviation. Whatever you're adding to it becomes the new mean. You can transfer it to 1 to 5, really whatever scale you want, but that is something you typically would do to present the results in like a hiring context, right? Other things that didn't come up, but you probably also want to kind of slip in some under development items. The best way to get new items in your database is to pilot test them, and the best way to get a realistic pilot testing is to administer them under testing conditions. And this is what, SAT and GRE and all those folks do. They give you a whole bunch of items that they're not even scoring, and you basically, freely dedicate your time to their validation efforts, and they make money off it. So this is something you want to do as well, though. You want to slip in some pilot items that you're not going to score as far as computing, theta, but you do want to collect that data so that later on you can merge them into the item bank. So you can item banks, like I said, about 3 times. So if you have 150 items, it's a pretty good start for 40 item test, maybe even 50 item test. If you only have, let's say you have a 50 item test, you only have 60 items, you'll gain a little bit from CAT. I mean, you're probably going to administer the best 50 of those 60, but it's really, the cost benefit of that is not strong, right? To really take advantage of the optimization algorithms and narrowing very quickly on theta, you need a pretty hefty item bank. So, really, you want to have an item bank that's big enough to let you choose items in a way that's going to get you to the precise data estimate relatively quickly. And that is it. That's some of the issues you have to worry about when you are, doing these setting up these CATs in practice.